Geometry, this is section 07 and 08. So about halfway through the page is section 07, and then the other section is 08 down below. Only the front side of the page, so we don't have too much to do. 07 is ordered pairs, and this is a very, very easy section, and that's why I've lumped both of them together. But they start out introducing ordered pairs in a very, very basic way. Over here, if you can't see these lines very well, go ahead and draw those in there. That's just talking about quadrants 1, 2, 3, and 4. So 1, 2, 3, 4 in that order, the way that the quadrants go. Ordered pair for point A, they're referring to this point over here. It looks like on the x-coordinate it's at about 5, and the y-coordinate is at -2. So that would be 5, -2 for part A. You probably could have done that yourself, but part B, graph B, it's -4, 3. So again, you're going -4 on the x-axis, 3 on the y-axis. So -4 up to 3. And then whenever you put a point on here, you always want to make sure that you name it, because we have multiple points going on at the same time. I want to make sure that each one of them have names, and you always name them with capital letters. So make sure you do that. And then it says, and state the quadrant in which it's located. Okay, if you haven't already done that, point B is in quadrant 2. Okay, you can either put Roman numeral 2 or you can put the number 2. I'm not too terribly specific on that. So Roman numeral 2 or number 2, and that gets us through example 1 for the ordered pairs. Example 2, they want you to graph 4 points that satisfy the equation. This guy right here, y equals 4 minus x, that is a linear function. All linear functions will have a y and an x coordinate, and the y and the x coordinate will be to the first power. So that's the main thing. We're out of focus now. If this was a quadratic function, it would be like y equals x squared. If it was a cubic function, it would be of the form of y equals x cubed, and so on and so forth. So this is a linear function. All linear functions, when you graph them, will look like straight lines. Okay, and they just want us to graph 4 points. So without using, or without cheating, I guess we're going to do that down below here, cheating, graphing the equation. We're going to graph 4 points. So when I do this, I always try to pick some x coordinates that are positive and some that are negative. Sorry, I keep going in and out of focus here. I apologize. I'm going to choose, let's choose like -4, -2, 0, 2, and 4. I'm going to go 5 points instead of just 4. So when we plug each one of those points into the equation, this guy right here says 4 minus a -4, because we're plugging that -4 in for x. Okay, so 4 minus a -4 would be like 4 plus 4, and our coordinate would be 8. So if I go to plot that, it would be at the point -4, 8, which is a little bit off my chart right here, that little dot. Okay, -2, so I'm going to plug 4 minus a -2, or 4 plus 2, which would be 6. So -2, 6, right there like that. If I plug 0 in, 4 minus 0 is 0, so is 4, so 0, 4, I have that dot there. If I plug 2 in, 4 minus 2 is 2, so I have the point 2, 2, right about there, and 4 minus 4 is my last point, is 0, so 4, 0, and I can connect my line, and it will look something like that. Okay, again, I kind of told you a linear function will look like a straight line. We could have picked any different set of points. We could have picked 1, 2, 3, 4 if we wanted to. I just like to do a positive and a negative range of x's to choose, because it gives me a good look at what the graph looks like over the span of all of the x's. So that's section 0.7. Very, very easy. So I've lumped that together with section 08, which is a little bit more difficult. Example 3 is just graphing, and example 4 is using substitution and elimination. So example 3, they want you to graph, and then we have to determine whether there's no solutions, one solution, infinitely many solutions for each one of these. And I'll explain that what that means here in just a second. But for part A, rather than treating this like the example that we just did above, where we're going to we're going to plug points in every time, we're going to cheat by graphing this first equation in an easier way. So we're going to start with the y-intercept, which is 3. There we go. Y-intercept is 3, so I'm going to put a dot on the y-axis at 3. Okay, and that dot's just going to stay there. Then this number in front of the x here, since there's no number there, there's a negative. We assume that that's -1. It's like an understood 1. That's going to represent my slope. That's the m part of it. Okay, and that means from this dot right here, I'm going to go down 1 and over 1. And -1 is a slope. If m equals -1, that's -1 over 1. Okay, we always put those whole numbers over 1. So that means I'm going to go down 1, over 1, down 1, over 1, down 1, over 1, down 1, over 1. And my linear function is going to look like this. Okay, I could also have gone up 1 to the left 1, up 1 to the left 1, up 1 to the left 1 in the other direction. Okay, that will give me that linear function. All right. The next equation, we're going to do exactly the same. So starting at -3 is my y-intercept this time. So I'm going to put my dot here. And this time my slope is 2. So if my m is 2, I have 2 over 1. That means I'm going to go up 2 for every 1 that I go over. Up 2 for every 1 that I go over. Up 2 every 1 that I go over. And my function is going to look like this. Or I could have gone down 2 over 1, down 2 over 1, and so on and so forth. Okay? All right, so I've got my 2 linear functions. And I'm going to now determine whether each system has no solutions, 1 solution, or infinitely many solutions. And what they mean by solutions is where those 2 lines intersect. Do they intersect in 1 spot, in no places, or in infinitely many places? Okay. Right now I have 2 lines that are intersecting obviously in 1 place. So this one has 1 solution, and you can abbreviate solution as SOLN. That is perfectly fine. Okay, so 1 solution, they're just intersecting in 1 dot like that. I'm going to put an X next to 1 solution because they're just going to intersect in 1 place. Now when it has no solutions, it's going to look like 2 parallel lines. Okay, so maybe you want to do a little visual like that. 2 parallel lines, because those 2 parallel lines are never going to intersect, so there will be no solutions. And then when it has infinitely many solutions, they will give you 2 equations that will, when you graph them, will look like exactly the same line. So it'll be really 2 lines that are directly on top of each other. That's what infinitely many solutions looks like. Infinitely many solutions because they are intersecting, those 2 lines are intersecting at infinitely many points. Excuse me. All right, so part B, we're going to do in the exact same way as we did part A, except this one is not in what's called slope-intercept form. We need to make sure the y is by itself on one side of the equal sign. Here the y is not. So for part B, the first equation, we have to get rid of that 2x. So I'm going to move the 2x to the other side by adding 2x to both sides, which should make y equals positive 2x plus 6. Okay? All right? And that equation is done. Let's go ahead and graph him, starting with the y-intercept. Y-intercept is 6, so I'm going to go up to 6 and put my dot. From there, my slope is 2. So m is 2, or 2 over 1. So I'm going to go up 2 over 1, up 2 over 1. I'm going off the graph, so in this case, I'm going to go down 2 to the left 1, down 2 to the left 1 in the other direction. And it's going to look something like this. Okay? The second equation, 3y minus 6x equals 9. Okay, I'm going to move this 6x to the other side by adding 6x. Okay, it's going to look something like this. 3y equals 6x plus 9. That 6x went from being negative on this side to positive on this side when I added him. Now there's one more step I have to do for this second one, and it's to get the y by itself. The 3 is in the way, so I have to divide everything by 3. When you divide by 3, don't just stop with that. Make sure you divide all 3 pieces by 3. So the 9 gets divided by 3 as well. The 3 goes away on the y, so y equals 6x divided by 3 is 2x, and 9 divided by 3 is 3. So I have 2x plus 3. And now we're going to graph him again. Okay, so starting with the y-intercept of 3, I'm going to go up to 3. Then from there, my slope is 2. Again, it's 2 over 1. All right, so I'm going up 2 over 1, up 2 over 1, or I go down 2 to the left 1, down 2 to the left 1, and it looks like this. Okay. Now, mine aren't completely parallel. They should be. Mine are kind of squiggly a little bit, but those two lines should be completely parallel, which means I have no solutions. Or you can put a circle with a line through it, because they are not going to ever cross at any point, so I will have no places where they cross. Now, if you look at the equations that we came up with, the ones that I'm boxing right now, that's what they look like in slope-intercept form. If you notice something about those two equations that is similar, they both have the same slope. Anytime you have an equation or two equations that have the same slope, they will always, always, always be parallel to one another and have no solutions. So that's what will happen. Both of them were 2x for the slope, so they are parallel and they were not going to cross. Okay? All right, they didn't give us an example of an infinitely many solutions one. If when we divided this out, this came out to be, let's say, 6 instead, those two equations would be exactly the same. Oh, look, we have the same line when we graph them, and there are infinitely many solutions. So that's an example of what it would look like if it was infinitely many solutions. You won't be able to tell that from the beginning equation, because these two equations look different, but when you put them in slope-intercept form, they will result in the same equation if it's infinitely many solutions. Okay? So that's what that will look like. All right, now, substitution and elimination. I very much prefer elimination over substitution, but a lot of people like the other one better, like substitution better. So when you're doing substitution, you need to first make sure that one variable is solved for. Okay, you might already be able to identify that right here in this top equation. Y is by itself. The y variable is solved for. Y is equal to negative 4x. Y and negative 4x are exactly the same thing. So if that's what y is equal to, and I see a y down here in the second equation, I can just take and plug that 4x in for y, because that's what y is. Y is negative 4x. So I'm going to go ahead and do that. In that second equation, I put 2, and instead of the y, I'm going to put negative 4x in parentheses, always, always in parentheses when you're plugging stuff in, plus 3x equals 8. Now, the reason why I did that was because now that second equation no longer has an x and a y in it. It just has x's, and I can go ahead and solve for x. So 2 times negative 4x, that's the operation I'm going to do first. That gives me negative 8x plus 3x equals 8. Okay, negative 8x plus 3x equals 8. I can put the negative 8x and the 3x together, making negative 5x equals 8. Yuck, this is going to be ugly. If I get the x by itself and by dividing by negative 5, divide by negative 5, I get x is equal to negative 8 over 5, which is kind of ugly. I'm going to go ahead and circle that as my answer because I've got a lot of work going on here. Okay. Now, I'm not done as soon as I find the x. What I'm going to do next is I'm going to solve for y. So I'm going to go back up to this equation up here. I could plug it into this bottom equation, but that one's a little bit uglier than the top one. So I'm going to plug this x from here into this top equation and solve for y. So if y is equal to negative 4 times whatever x is, and x is negative 8 over 5, I'm going to plug that in, okay, and then I will solve. So make sure that when you do this, the 4, you're remembering that that actually means 4 over 1. I have a lot of students that will like to take 4 times 8 and 4 times 5, which will give you like 32 over 20. No, that's not right. Don't do that, okay? It's actually 4 times 8, which is 32, over 1 times 5, which is 5, okay? Now we have to decide whether this is going to be positive or negative. So I'm taking a negative times a negative, which makes a positive, So the y equals positive 3 or 32 over 5. I would just leave it as 32 over 5 rather than dealing with a mixed number. You can convert that if you want to, but I'm just going to leave it. The way I like to write the answer, though, is in an ordered pair, like we do above. So it will be the point negative 8 over 5, comma, 32 over 5. And we are done. That is the answer. Okay? So that was substitution. You want to make sure one variable is solved for in one of the equations and then plug it into the next one. Okay? Part B, elimination. Okay, this is the one I like the best. You want to choose, in both of these equations, one variable to eliminate, okay? And sometimes it's obvious which one you want to eliminate. Like, for example, sometimes this will say like 3x, and this down here will be negative 3x. If I would add those two equations, top and bottom, the x would cancel out really nicely. Here it does not. So I have to choose which variable I want to eliminate, okay? Let's just go ahead and do the x. We're going to have to do a little bit of work to this example because they don't just directly eliminate out, but it's gonna be all right in the end. Okay, so 3x and 4x, those are the values that I'm focused on. Okay, 3 and 4, the smallest number that 3 and 4 both go into is 12. So what I want to do is I want to make one of these. The top one, I want to make 12x. And let's say the bottom, I want to make negative 12x. Okay? You see how those two would cancel out to be 0? I want to get rid of or eliminate the x. Okay? So to get 3x to become 12x, I have to multiply this whole thing through by 4. Okay? So I took 4 times 3x to get 12x, right? I'm going to take that 4 and distribute that through for all of 3 of the pieces. Okay, so 4 times 5y is a positive 20y, okay? And then I do 4 times 7, which is 28, all right? Now I've taken 4 and I've multiplied through by this whole piece, that whole first equation, okay? Then the second equation, I want that 4x right here to become negative 12x, okay? And the negative 12x, to get that, I have to multiply 4 by a negative 3. Negative 3 times 4 gives me negative 12. So I'm going to take this entire equation and multiply through by negative 3. So negative 12x is what I get with the first term. Negative 3 times 2y is negative 6y. And negative 3 times 0 just stays 0. Okay? So I've redone both of those equations so that one of the variables will cancel. All right? Then you're just going to simply add the equations together, top and bottom, okay, with exactly the same signs as are there. So 12x minus 12x, that's going to get your x's to go away. So you have no x's left. All right? If at this point you still have an x left over, and that was the one that I was trying to eliminate, then we probably did something wrong because one variable should eliminate at this point. Okay? Then we've got 20y minus 6y. 20y minus 6y is 14y. Make sure that y goes with it. The y doesn't cancel out when you subtract. Just the numbers subtract each other. So 14y, and then 28 plus 0 is 28. Okay, this is going to come out as a nice number. To get y by itself now that I have no x's, I just divide by 14, divide by 14. Y equals 2. Okay, I'm going to circle him. Now, just like we did in this other example, I'm going to have to plug that back into one of the equations up above. Let's in this example, let's do this second equation. So let's do 4x plus 2y equals 0, because I like the 0 in there. So 4x plus 2 times whatever y is, and we said y was 2, equals 0. Okay? 2 times 2 is 4, so I have 4x plus 4 equals 0. Right? To get the x by itself, I want to move this 4 to the other side. So 4x equals negative 4. And I'm going to divide both sides by 4, divide by 4, x equals negative 1. Okay? And I'm going to write both of those answers together as negative 1 comma 2. as an ordered pair, and that's my final answer. Okay, now that was substitution and elimination. If I went too fast on that, rewind or go back and you can figure these steps out again. But one thing I want to talk to you about before I quit this video is this point right here, that ugly point that we came up with, and -1, 2. Why do we care about those 2 points? Yeah, that's my answer, but what's the significance of them? Okay, the significance is this. If we were to take, let's say, like these 2 equations right here and graph them like we did up above here, those 2 lines, these 2 linear functions, would cross at this point. Okay, same thing with these. If we would graph these 2 lines right here, those 2 linear functions like we did up here, it would be 2 lines that cross each other at this point. So I might ask you that on a test or a quiz. Why do I care about this answer? You should have that drilled in your head from Algebra 2. I care about this answer because that's where these 2 linear functions cross each other, or these 2 linear functions cross each other, okay, if we were to graph them. All right, and that's basically it for section 0708. Again, if I went too fast through that, go ahead and rewind, and you can watch this video again. And that's all I have.